Okay.
Good morning, everyone. Today I'm going to talk about the first order logic. First, I'll say something about the knowledge representation, and then I will introduce in detail what first order logic contains, what are the elements, and then I'll talk about an alternative semantic for first order logic. In the knowledge representation, I'll talk about the difference between programming language and propositional logic. And then I'll talk about the disadvantages of propositional logic. Then I'll combine the best of formal language and natural language to generate the new kind of the language, the first order logic. And then I'll briefly introduce the elements of first order logic. The difference between programming language and propositional logic. The programming, and actually the whole paragraph is trying to say the advantage of propositional logic over the programming language. First, the programming language is not as expressive, and it lacks the general mechanism for deriving facts from other facts. The programming languages do not have the functionality of inference. You cannot perform any inference on programming language. It runs by itself simply. And second, the propositional logic uses a declarative approach in which the knowledge and inference are separate, and inference is entirely domain independent. This is a very good characteristic of the propositional logic. And the third, the programming language is not as expressive as the propositional logic, and it cannot, and so as a consequence, the programming language cannot handle partial information, while the propositional logic can. And finally, propositional logic has the property of compositionality, which means the meaning of a composite sentence is a function of the meaning of its part. When you combine all the meaning of its parts, you get the meaning of the whole sentence. But propositional logic also has some disadvantages. It lacks the expressiveness power to concisely describe an environment with many objects. To handle this kind of objects, you have to write the same rule for each object in the model again and again. And if we combine the best of formal and natural language, we can get the first order logic. And the elements of the first order logic, includes object, which is expressed using noun or noun phrases. They refer to things. And the second element is relation, which is expressed by verbs and verb phrases. They are assertions and statements about objects in the environment. And third element is function, which also means objects, but it takes objects as input and returns an object. We should note that there are many kinds of relations, but two kinds of relations that we use very common are the binary relation and the unary relations. The binary relation takes in two objects as parameters and return one object. It can be viewed as a set. It does not return objects. It is an assertion, a statement. It can be viewed as a set of tuples of objects that hold in the relations. a set of binary tuples altogether. They form a binary relation. And a unary relation can be viewed as a set of objects that hold a property. You see, a different word, property. So all the objects that have the same property are put together under the same unary relations. And this is what the unary relation means. And now I'll give some detailed insight into the semantics of first-order logic. I talk about a symbol, the term, the atomic sentence, complex sentence, quantifiers, and equality. First, the symbols. For objects, we use constant symbols. For the relations, we use predicate symbols. And for the object functions, we use function symbols. Here are the examples. And when we are trying to define a problem in first-order logic, we have to specify two things. First is the symbols in the problem, and the second is the meaning of the symbols. So what are the symbols? What are the constant symbols, predicate symbols, function symbols, etc.? And we have to specify the meaning of them. Here is an example. This is the example in the textbook. You can find it in the chapter 8. What we have to pay attention to is symbols are only symbols. They do not have meanings themselves. And the meaning of the symbols and the symbol themselves are separate. The meaning of the symbol are specified by human beings by intended interpretations. And which the mapping between symbol and objects in the model are also specified by human beings with extended interpretations. There are many possible intended interpretations and extended interpretations for a problem. And for example, in the example problem in chapter 8, the Richard and John problem, there are 25 possible intended interpretations for constant symbols, because we have two constant symbols here, and we have 5 objects in the model. So 5 multiplied 5 is 25. There are 25 possible intended interpretations. What does it mean? So Richard does not necessarily mean Richard the Lionheart. It can mean the evil King John or the Chrome, etc. The meaning is not is specified by human beings. It's not naturally associated with a symbol. There are many possible models for a problem. There are many infinite number of models for a problem, and the models difference varies by the number of objects it contains and the way the constant symbols map to objects, what we call extended interpretations. And it is possible for multiple constant symbols to refer to one object, and it is also possible for some objects is not associated with any constant symbol at all. And because the number of models is unbounded, and checking the entailment by enumeration of all possible models is not feasible in first-order logic. And although there are many possible models, it is up to the knowledge base, not the intended or extended interpretations, to rule out models that are inconsistent with the knowledge. So, by the definition of extended interpretations and intended interpretations, there are infinite number of possible models, and many of them are ridiculous according to the knowledge base. But it is up to the knowledge base, not the interpretations, to rule out the ridiculous models. And next is the term. A term is a logical expression that refers to an object. So we can view a term as an object. There are two types of terms, constant symbol and function symbol. And here is an example. And atomic sentences, there are two types of atomic sentence, term and predicate symbol. And obviously term includes the objects and function symbols, the constant symbols and function symbols. And here is an example. And what we need to pay attention to is that atomic sentences can have complex terms as arguments, as is shown in the example here. And atomic sentences is true, and atomic sentence is true in a given model if the relation referred to by the predicate symbol holds among the objects referred to by the arguments. So there are infinite many models for problems, and for some there are many obviously ridiculous models. In such ridiculous models, the relations may not hold among the objects when they are supposed to. And for the complex, we can generate complex sentence by connecting the atomic sentences with the logical connective, or and implication, etc. And this is very important. And first order logic is special because it has quantifier. Quantifier express the properties of the entire collection of objects instead of enumerating the objects by name. A universal quantifier, it means that for all objects in the model, the sentence P hold. And the and example and implication is often used together. And we know that, so why is this the case? Because we know that the implication is false only when the premise is true, but the conclusion is, and when the premise, oh, that's not correct. I'll change it right now. Quite opposite. When the premise is true and the conclusion is false. Okay? Only when the premise is true and the conclusion is false. So an implication of universal quantifier means that in the model that is right, that is correct, that is not ridiculous, when the premise is false, so there are many different possibilities of objects that can be applied to the sentence after the universal quantifier. For those whose premise is false, the implication is true, and it means that it says nothing about the object. And when the premise is true, the conclusion must be true, because it is not a ridiculous model. It is not a wrong model. It is correct. For example, we have an implication here, and we can apply all possible objects in the model to this sentence, and we see that for the sentence whose premise is correct, the conclusion is also correct. And for the other sentences whose premises are wrong, the whole implication is true, which means the sentence does not say anything at all. So the implication as a whole is true. and then the existential quantifier. So it means that in the model that is correct, that is not ridiculous, consistent with the knowledge base, the sentence is true for at least one object X in the model. We should pay attention that the implication is naturally connected to use with N and with all the possible for the universal quantifier. And the N symbol is the natural connective to use with the existential quantifier. And why? Why is that the case? Because if we want to use the existential quantifier with the implication to ensure that the sentence is true, what we have to do is to find one object that makes the premise false. This is false. And this is very, very easy. Which means the whole sentences will be too weak. In the other case, if we use the universal quantifier with the N, the overall sentence will be too strong. The assertion will be too strong. And we can nest the quantifiers. What we should notice is that the order of quantification is very important indeed. They can have completely different meanings. We can see from the examples here, the two sentences have different meanings. And second, the variable belongs to the innermost quantifier that mentions it. And it will not be subject to any other quantification. For example, the variable x here belongs to the innermost quantifier that mentions it, which is here. And it will not be subject to any other quantifications, including this one. Also, for convenience, you can replace this line with this. This is quite natural. And for equality, we can use equality to signify that two terms refer to the same object. For example, this line means that father of John and Henry refer to the same objects. And it can also be used with negation to say that two terms are not the same. For example, Richard has at least two brothers. We write in these first order logic expressions, we have one brother, we have Richard has at least two brothers. Okay, it's a if. This is also incorrect here. Okay. So, if we simplify the meaning of the whole sentence in one words, in very simple words, we can say that Richard has two different brothers. This is exactly what it means. And, oh, it's also not correct. It's not equality now. There is an alternative semantic. The first order logic I introduced before do not use a very complicated semantic, and it does not use the semantic here. This is the semantic used in database language, such as the SQL, etc. And it is based on two or maybe three assumptions, the unique name assumptions, which means every symbol refers to a distinct object. And the closed world assumption, which means atomic sentences not known to be true, are in fact false. And each model contains no more domain elements than those named by the constant symbols, which means there are no objects which are not associated with any constant symbols. And this is the semantic used by Prolog, as I shall describe in the next chapter. This is all for this chapter. Thank you.
Enemy board